Hello, everyone. My name is Szentgyorgyi, and today I am very honored to be interviewing a very special space champion, Dr. Andrew Szentgyorgyi. He is currently working at the Smithsonian Astrophysical Observatory and occasionally teaches at Harvard University's Department of Astronomy. He has worked in a number of astrophysical areas, including neutrino astronomy, very high energy gamma astronomy, and X-ray astronomy. For the last 2 decades, he has measured and focused on optical high dispersion stellar spectroscopy with a focus on precision measurement of stellar radial velocities. He is also currently the principal investigator of the GMT-Consortium Large Earth Finder, the first light instrument for the Giant Magellan Telescope. He is currently exploring the potential of G-CLEF to detect biomarkers in the atmosphere of habitable-zone exoplanets, which is very exciting. In addition to stellar astrophysics, his scientific interests include optics, especially vision and atmospheric phenomena, and musical acoustics. I'm so excited to be able to understand his journey on a deeper level and understand how he got into the space industry. Welcome. Thank you so much for taking some time out of your busy schedule to conduct this interview.
Well, thank you for having me.
Yeah, before we get into understanding, your journey into the space industry, first I'd like to understand more about your typical day. What do you currently do and how does it run?
Well, for a long time, I was just like everybody else on Earth that was working. Fortunate enough to have a job in the last year. I was working from home, and about the trouble is that I come from an era when everything was on paper, and so I got permission to go back in the office 4 days a week. Oh, I don't know, 6, 7 months ago, because there's all this stuff, and mechanical drawings. But normally, again, this is exceptional times. These days, I spend an incredible amount of time on Zoom and Meet and WebEx and stuff. I have a team of, I don't know, there are probably 50 people affiliated with building G-CLEF. And in the old days, we just get in a big room and, people raise their hands and go draw on the whiteboard. And now things require kind of specialized interactions. And so you find that everybody says, oh, how about tomorrow? And I say, well, I've got 15 minutes between 12:45 and 3. The thing to realize is that as you work on big projects, as you get older, you start, it sounds like kind of a cop-out. You stop doing so much of it yourself, and it's not because you're not capable of doing it yourself, or you couldn't, I think I'm still pretty good at optical design, but the idea is to sort of spread yourself out. So an awful lot of what I'm doing is mentoring and technical meetings, giving talks, and then sometimes having the pleasure of talking to people like you.
Wow, that sounds awesome. Yeah, I definitely agree with, once you start getting more deeply involved, there's so many different projects you're overseeing and are a part of. It's really difficult to do every single step. So I completely understand where you came from. And so I'm curious more on what is the most exciting project or research, if you had to pick one, that you've ever worked on or are currently working on?
Well, it's always that, I'm always doing what I'm doing because it's the most exciting. I think right now it's the most exciting thing in the world. And so right now, G-CLEF is, the most exciting thing to me. There's one, they've discovered that the star that's closest to the sun, Proxima Centauri, has an exoplanet orbiting it. It's very different than the sun. It's a very cool star. So it's a lot redder than our sun is, but it has a planet that's orbiting in what's called a habitable zone. So that means this planet is just the right distance from that star for there to be liquid water on the surface of the planet. Okay. And we tend to believe, it's a sort of anthropocentric view of the universe, but we believe that you probably need liquid water for life-sustaining chemistry. There are a lot of reasons for that. One kind of simple thing that we forget is that water is we believe that you need liquid, first of all. And water is actually one of the few common liquids that floats when it freezes. So when you had aquatic animals at the beginning of biogenesis on the Earth, if ice was denser than water, all the ice would sink and then lakes would freeze solid. But instead, lakes and oceans don't freeze solid. They form an icy crust on the top. And so aquatic animals can be dormant. So anyway, this planet is in the habitable zone and is very, very close to us. So it's the brighter something is, the easier it is to learn more details about it. It's not close enough to take pictures of it yet. But there is this chance that we might be able to look for evidence of life on that planet in the next 5 years, well, not next 5 years, but next 10 years. Most people believe that to really do a search for life on planets orbiting stars other than the sun will require these really gigantic telescopes that are only being built now, that have primary mirrors that are 25, 30, and 39 meters in diameter. But there is an opportunity with this thing, because of this one planet, exoplanet, because it's so close, to actually look for signs of life with existing telescopes if we could put G-CLEF on it.
Wow, that, I feel like always the topic of finding life outside of Earth, and it's just really exciting for everyone, and discovering new exoplanets. I think it's always exciting for, all people of all ages. And so for the younger audience here, could you explain, like, how are you guys able to, discover these different planets? How are you able to determine what its composition is? Like, how do you know it has water and it's not like a gaseous planet?
Okay, well, let's see, that's a lot of things at once. The first thing to actually remember is we always, people generally talk.
Can I ask you a quick question? What time will you leave here to go to Tarzan?
About half an hour, could be.
At 4:30?
Yeah, right. Okay. The first planet orbiting a star other than the sun was not a star like the sun. It was a pulsar, and so it's a neutron star. That has burned up all it's a star that burned up all its nuclear fuel, and the core collapsed, and now it's this very strange kind of material that's neutron matter, and it was the first. It has a planet, but the first exoplanet orbiting a solar type star it was 51 Pegasi b, and that was discovered by what you mentioned briefly a while ago, the radial velocity method. And in the radial velocity method, you don't actually detect the planet. The sun and all the planets don't all go around the sun. The sun, there's a common barycenter. There's a center of mass of the whole solar system. And so the sun, all the planets are going around the center of mass, but the sun is always also going around the center of mass too. But, like a big fat person that's swinging a little tiny baby around, the baby goes around a lot, but the big fat person doesn't. So, and so the sun is orbiting with a very small velocity shift back and forth. But it turns out in the last 20 years, we've gotten so good at measuring those radial velocity shifts, where the star is going back and forth this way with respect to what we call your line of sight, that we can now measure a star with 30 centimeters a second velocity shifts. And we do that by measuring the change in the spectrum. There's a thing called the Doppler shift. And so when something is approaching you, it becomes a little bit bluer. And when it's going away from you, it gets a little bit redder. And so if you can measure, if you're very, very good thing to measure that your stellar spectrum about, you see the spectrum with time, whatever the period of the orbit is, going back and forth, getting redder and bluer and redder and bluer as the star goes around like this. 10 centimeters a second, it's the same way a radar gun that a policeman has works, which bounces a radar, which is just another form of light off a car, and the Doppler shift of that light coming back to the policeman tells you how fast you're going. But the speed of the sun in response, the maximum, that sun reflex motion, the amount of maximum minimum speed, maximum approach and recession speed is 10 centimeters a second if the Earth was the only planet in the solar system. And that's as fast as a Galapagos tortoise walks. So it's not, it's really a very small number. Now we now have lots of other ways of detecting exoplanets. One particularly handy way is what we call the transit method. So if it turns out that the orbit is exactly aligned so that as the planet goes around the star and it comes right between you and the star, that planet casts a shadow as it passes in front of the star. So you look at the brightness of the star, and if you see it getting dimmer for an interval of time that's consistent with the planet orbiting it, and it happens over and over and over again, then you can detect an exoplanet that way. It's called the transit method. And there are two prominent number of satellites that have increased our catalog of exoplanets exponentially. There's a thing called the Kepler mission, and it found thousands of when we do them by the radial velocity method, sometimes it takes years to actually really accumulate the evidence that you've got an exoplanet. Whereas Kepler found thousands of them by the transit method. And they actually find planets that are almost as small as the moon. And there are a couple of other different ways. I'm not going to go into it. But the thing is that the way we look for life, it's worth understanding a little bit about how we do that. And, the Earth's atmosphere is very unusual because it's about 21% oxygen. It's oxygen in the form of diatomic oxygen, so it's two atomic atoms stuck together. And the reason there's diatomic oxygen in the Earth's atmosphere is because there's life on Earth. If you leave an atmosphere alone, if you take an atmosphere and somehow fill it up with a lot of oxygen and leave it alone, oxygen is sticky stuff. It likes to form oxide, so it likes to make rust. All the sand on the beach is silicon oxide or dioxide. I don't know exactly. So if you want to constantly replenish the balance of oxygen, you have to have something alive that's taking the oxygen that's in other compounds and ejecting it back out into the atmosphere. And so one of the easiest things, the lowest hanging fruit, would be to look for the presence of diatomic oxygen in exoplanet atmospheres. And what you do, the way you do that is you have a spectrograph like G-CLEF, and the light that comes out of the sun, the planet, has a very particular set, has some kind of unusual features. One of them is the feature, there is sort of this broad, if you hold a prism up and let the sun's light go through it, you see this smear of light. But and it's like kind of smooth, it gets dark at one end and then blue and then green and then red and then goes dark again. But if you had a super prism, which you can think of G-CLEF as, and it really spread the light out a lot, you would notice that there's little dark things in there. There are some colors that are not present in the spectrum of a star. And those are called spectral absorption features. And a star has a certain set of spectral absorption features. But when the planet comes between you and the star, the light has to come through the planet's atmosphere. And there's a different set of spectral absorption features. And it turns out there's a really good spectral absorption feature that oxygen 2 produces. So what you have to do is first measure the star's spectrum really, really well so that you know what absorption features belong to the star. And then you watch for this oxygen thing to appear when the planet goes between you and the star. And so the first search one of the first searches we're going to do, there are a couple of different, James Webb Space Telescope, JWST, James Webb Space Telescope. We'll look for different things. I think they'll probably look for methane, which is something that cows burp out and is a sign of bioactivity. And so there are a number of different ways to do it, but they all sort of boil down to what we call these spectral detection methods.
Yeah, thank you so much for explaining that so specifically. Like, I was able to get a way better understanding than what I had before. I think when ever since I was a little kid, always was interested in astronomy, but never actually knew how we were able to explore, what's outside of our planet without actually us being able to see. So being able to have these spectrums, like you were mentioning, giving us certain detections or like patterns, it's just a long process, but that's really exciting to see come to life. And when you guys do discover something, I'm sure it's an amazing feeling.
Yeah, it's that increasingly, at least astronomy, but it seems like all of science, there seems to be sort of a great multiple disciplinarity to what I think is the most interesting kinds of science we're doing today. So, we have my friend Dimitar Sazalov started the Origins of Life initiative at Harvard, and I participate in that some too. And so there are people that are molecular biologists, people who drive the rovers on Mars, people that are doing just pure chemistry, and then there are astronomers like me, people building instruments and stuff. But we all work together fairly closely, and it's a powerful way to think about things.
Yeah, science is very interdisciplinary. And, through this interview series where I'm trying to explain a lot of space, I feel like space I was able to discover is very, very interdisciplinary. Like there's not one job we don't require. Like every job you would imagine in the real world is needed just itself in the space industry. The different types of scientists, the different types of engineers, literally just,
Absolutely.
it's great. Yeah, the policy side of things in order to get the budget to do things. Like it's like a whole new world. So I definitely, I believe that every topic is interdisciplinary, especially science and space. Yeah.
Right.
And so I'm curious, what intrigued your interest for astronomy, or just really in general the sciences, when you were a young child?
Well, this is sort of my dark secret is that I, when I was in grade school and high school, science was really easy. I mean, I didn't, but I never really thought about being a scientist. Most of my family are artists. My brother writes for Hollywood now. And so I always wanted to be a painter. And I went off to Syracuse University School of Art when I left high school. I didn't ever actually finish high school either. This was, the 1960s and 70s. And I sort of finished my coursework at high school, and I never graduated. I only went for 3 years. And I went to art school. And unfortunately, my father, who's a writer, was having a bad economic period, and I was told to leave Syracuse University Art School until I could afford to pay the tuition. So I was expelled. And so I was working as a painter at night, and painting, taking all these different funny jobs, and did all kinds of things. I worked as a draftsman. I took care of geriatric mentally challenged people. At one point I had interviewed at Syracuse University to work in the bookstore, because the bookstore had a huge art department. You get this great discount on art supplies. In those days, a tube of cadmium red paint cost $3.25, which was just, when I got paid $100.25 an hour, that was a lot of money.
Yeah,
so, yeah. 50% discount. So I took the job, and I was about to start it, and the employment office said, "Well, there's also this job in the physics department. Would you like to work there?" And I said, "Well, does it involve? Do you get access to the machine shop?" Because I'd always wanted to learn how to, work machine shop tools. And they said, yeah, it does. So I went over and interviewed, and they gave me the job, and my salary went up to $159 every other week. And they said, "Now, before we give you this key to the machine shop, you know how to use everything in there?" And I just lied, and I said, "Yes." I went down there, and there's this old German technician I worked with, and he kept saying, "Somebody's using that machine shop that does things in very unusual ways." But, after a while, I discovered that there were these people called physicists. And they didn't need to have a job during the day to do physics at night. They just, want to work in the morning. And, physics seemed so, it's much easier than painting. I mean, you get a blank piece of canvas, and you've got these tubes of paint, and you have to figure out something that's going to be intellectually and emotionally significant to other people. And, with physics, you just come in the morning and you look at your calculation and you keep going, or your lab equipment. And so I started out on high energy physics, which is, the kind of science they do at CERN, super collider. But, they've got that kind of industrial grade after a while, because the collaborations got so big, it didn't seem attractive. So when I went to graduate school, I changed to, I did theoretical astrophysics for a while, but theory turned out not to be my special thing. It's important to know what you're not good at. And so I did cosmic ray physics. I worked on gamma ray astronomy. And then when I got done with graduate school, I sort of got tired of I don't know, I wanted to launch things into outer space. So I became an assistant professor at Columbia University and worked in X-ray astronomy for a while. And then I came up to the Smithsonian in 1989. My son was born. My wife, we needed to live someplace where we could both have a job. So I came to the Smithsonian. My wife eventually joined me at the Smithsonian. And I started doing X-ray astronomy, doing optics in particular, but then I changed to, there's a friend of mine who's building this big robot to be able to do 300 different spectra all at once. So it was a multiplier for the telescopes. It was like having 300 telescopes instead of just one. And it was a very complicated robot. So he asked me if I come work with him. And that's sort of how I got into optical ground-based telescopes and spectroscopy. And I don't know, I just sort of started doing high dispersion spectroscopy.
Yeah. Did you have obstacles when trying to pursue your passion, maybe even outside of college, like trying to get you different jobs? And if you did have obstacles, how were you able to overcome them?
Well, yeah, I mean, the plain truth of the matter is that I had to work for 4 years because I owed a lot of money, and I needed enough money to go back to school. And so I was a freshman when I was 21. And so I remember being an undergraduate and everybody else is 18, and they've just come out of high school and they know the whole periodic table and everything. And I've been working at a steel mill and stuff. So it took a lot of catch up. But, I like doing what I'm doing. There are obstacles, but everything's going to have obstacles, I mean, my one piece of advice is that, so we're getting up on half an hour, and I've said this many times before to, people like yourself, when I've done a couple of things like this, is that, you spend most of your life, the best hours of assuming you're employed, which, hopefully you will be, you spend most of the best hours of your day at work. So it better be fun, and my mantra is always that, as far as I know, you only get one life. If you might as well spend it on something that's meaningful to you and hopefully has some impact and you think matters. And if you, otherwise things take care of themselves for them. Terrible things happen to you, but you can kind of shrug them off if you're doing something that matters.
Yeah, I think always having like, if you follow your passion, I guess like you were saying, regardless of the obstacles you have, what you're doing is something you enjoy, something that's valuable, and so you will overcome those obstacles to pursue your passion, which I think is just amazing advice for everyone. Like, regardless of whatever age, if you find out your passion at like 50, yeah, you can keep going, you can change your track and you can go. And I mean, there's no boundary to age, but always remembering your passion and not being afraid for change is really important.
One real important thing that you see, I always thought I wanted to be an artist until I don't know, I was about 19 or 20. And it's really important. Two things are really important. One of them is to be open to new things. That's why I'm not really super in love with people going to college in a professional program that they're, when they come out, they're just going to know what they're going to do for the rest of your life, because you never know what you're going to do for the rest of your life. That's an incredibly important thing. And the second thing is that it's really good to get a work experience. I mean, the fact that I had to work for 4 years was very, very instructional to me, because, when you're studying things in school, it can be fun, but when you have to do it for 8 hours a day, it may not be fun. So it's really good early on when you think, oh, I want to do this with my life, that you get it, you kind of go out and try it a little bit and be open to changing your mind. Because I, for instance, discovered that I hated, one of my first jobs was being a draftsman. I thought, that's a good way for an artist to make a living. But boy, did I hate sitting at a drafting table all day. And so, when you're in school, it's all theoretical, and then you get out in the real world and it's not theoretical anymore. That's what you're going to, put on your whatever clothing you put on for your job and then spend the next 8 hours doing it. And it's not the same as learning about it in a classroom or doing it the first or even third time. You know, it's when you do it the 600th time, you still like doing it.
Yeah. And I feel like during, even during high school for students to be able to go through like summer programs or, internship opportunities or like maybe listen to different, like, because nowadays social media is so prevalent in everyone's lives. So, utilizing the platforms to understand how a day in a life of like, whatever profession you want to be in looks like and understanding that better is so important. And so I'm curious, did you have maybe a mentorship, an internship, or maybe like a person who you looked up to help you, kind of guide your path?
As an undergraduate, yeah, my undergraduate advisor was a very nice guy. We weren't, super close. My graduate school advisor was very influential. I had 3 guys that all thought they were my advisor. They were very sweet. But I had this very funny, my thesis advisor was a very funny guy named Ugo Tamarini, and he was an Italian Jew who never finished his PhD. And he was a very inspirational guy. When I was starting out, I wasn't the best student. And he's very encouraging and gave me the space. And there were 2 other guys named, one of them was professor at University of Hawaii named John Learned, and a guy named Bob March, who wrote Physics for Poets, he was very big on, the humanistic aspects of science. And so since I came to, I sort of came to think, I didn't come to science. I wasn't born with the slide rule in my hand. I'm the only person in my family that's ever mastered calculus. My brother passed it in high school, but so it was nice to know that you didn't, you didn't have to, start out with your HP calculator in the cradle.
Yeah, and what you were saying is, a part of the interview series mission is really to show students that you don't have to, grow up in a certain environment or look a certain way or come from a certain background in order to pursue a certain career, whether it be, just because you don't have a certain economic status or like because of a certain gender identification or ethnicity. Like none of that should be a factor into choosing a career you want to do, because literally every job is available for every single person out there. And, highlighting stories like yourself where you weren't born with that calculator or that mindset like, oh, I'm gonna major in calculus and I'm gonna go into physics. Like you didn't have that idea. Your background was in the arts. But growing up and finding your true passion and love for physics and astronomy is something that you're able to discover. And every single person out there can do that as well. So thank you for sharing that story with us.
No, it really is, important to realize that just because everybody, I've always felt that doing what everybody else wasn't doing was probably the best strategy, because you had the most room to grow and discover things. But just because everybody else is doing something the same way doesn't mean you have to. And sometimes it's your job to teach other people that there are other ways of doing things. It's so what year in high school are you in?
I am currently a junior, and so I'm really interested in space medicine. So a part of the thing I really try to stress through the interview series again is interdisciplinary studies, like you were saying. No one in my area is interested in space medicine. I mean, even if they are, they don't know what it is. If I ever tell my teachers, even my biology teacher, I'm interested in space medicine, she's like, what, space medicine? And so, going into like a unique study that a lot of people in my area don't know about, and combining both my interests together is something that kind of relates to what you were saying, which is, create your own job. If it doesn't exist already, or there's very limited people, that just means more, room for growth. I read this article saying how in like 10 years, we're going to have millions of new jobs that don't currently exist right now. So the door is open for every single person out there to create their own jobs. So you could be the first of everything. And I'm a strong believer of that.
No, if I was to make a list of things that didn't exist that we use, if I said to my father, oh, I'm just going to listen to the radio with my computer, and he could say, well, how do you connect it? Where's the antenna? I say, well, no, it just comes through this little fiber optic. It would astound him, and that was, he died 20 years ago. So it's quite remarkable. The world will be different.
Yeah. Yeah, definitely. So I want to thank you so much for, taking your time to do this interview and giving an insight into your journey for the rest of us. I was truly an honor talking with you about your research, your work, your passion, and your journey into the space industry. So thank you for all you do.
Well, you're presumably going to go college visiting soon, right? And when people can visit, well, if you we have there are a couple of schools in Cambridge a person can consider going to, and if you find yourself in Cambridge, I'm over at the Smithsonian's. Come and knock on my door, okay?
I definitely will. Thank you.